For much of human history, space was a place of myth, the domain of gods, dreams, and unreachable stars. Then, in the 20th century, we broke the barrier. We built machines that defied gravity, launched men into orbit, and touched the moon. But even then, space was something rare, something fragile, something prohibitively expensive. Every launch was a one-way trip. Rockets were built, fired, and discarded. Complex vehicles, the height of engineering, fell into the ocean or burned in the sky, never to be used again. It was like building a skyscraper and demolishing it after each use. No wonder access to space remained limited, the playground of governments, militaries, and only the wealthiest of institutions. Then came a radical idea. What if rockets could be reused, not just in theory, but routinely? What if they could land safely, be turned around quickly, and fly again, just like airplanes? It sounded impossible. And then SpaceX made it real. Let's understand the problem that SpaceX set out to solve. In traditional spaceflight, a rocket's first stage, which provides most of the thrust, detaches once its fuel is spent. It either crashes into the sea or burns up in the atmosphere. The upper stage continues with the payload into orbit. That's it. Billions of dollars lost in minutes. NASA's Space Shuttle attempted partial reusability in the 1980s, recovering the orbiter and solid rocket boosters. But refurbishment costs remain sky-high. Each launch still cost over $1 billion. Time between missions? Often measured in months or more. This model simply wasn't scalable. If we were ever going to launch thousands of satellites, send cargo regularly to the moon, or transport humans to Mars, we needed a new system. A system that could land, refuel, and relaunch again and again. SpaceX believed that such a system wasn't just desirable. It was essential. When Elon Musk founded SpaceX in 2002, the idea of reusable rockets was considered unrealistic, even laughable by aerospace veterans. But Musk wasn't an aerospace veteran. He was an outsider with a disruptive mindset and a deep conviction. If airplanes weren't reusable, no one could afford to fly. So why should rockets be any different? Early on, SpaceX focused on smaller launchers, the Falcon 1 and then Falcon 9. The Falcon 9 was different. It was designed from the ground up with reusability in mind. The first stage included landing legs, grid fins, and multiple engine restart capability. In the beginning, attempts to land boosters failed spectacularly. Some crashed, some missed the target, some tipped over just seconds before touchdown. Each failure was public and often mocked. But SpaceX treated failure differently. Every crash was data. Every explosion was a lesson. And most importantly, every attempt brought them one step closer. Then, on December 21st, 2015, they made history. A Falcon 9 first stage returned to Earth and landed upright at Cape Canaveral. Suddenly, the impossible was possible. So how exactly do you land a 50-meter-tall rocket, falling at thousands of kilometers per hour, on a tiny pad, either on land or in the ocean? The process is a ballet of precision and physics. First, after stage separation, the first stage flips 180 degrees to orient for re-entry. Then, cold gas thrusters, essentially small nitrogen puffs, help stabilize the booster. As it falls through the upper atmosphere, it deploys grid fins, metal cross-like structures that act like rudders, steering the rocket through the air with surprising accuracy. Then come the engine burns. The boost back burn pushes the rocket back toward its landing target. The re-entry burn slows it as it slams into the thickening atmosphere. And finally, the landing burn, the final deceleration, performed by 1 or 3 Merlin engines, to bring it to a soft touchdown. All of this happens autonomously, guided by onboard computers using GPS, inertial sensors, barometers, radar, and pre-programmed flight paths. No pilot, no joystick. And let's not forget the landing legs. 4 carbon fiber reinforced aluminum arms that deploy at the last second to catch the rocket like a dancer landing in point. Every second, every action is timed to perfection. A split-second miscalculation means catastrophe. But when it works, it is poetry in motion. Not all boosters can return to land. Some missions require the rocket to fly too fast or too far downrange, which doesn't leave enough fuel to reverse course. That's where the drone ships come in. SpaceX designed and built massive autonomous landing platforms, essentially robot barges, that wait hundreds of kilometers out to sea. Names like "Of Course I Still Love You," "Just Read the Instructions," and "A Short Fall of Gravitas" add a touch of sci-fi humor to a very serious engineering challenge. Landing on these ships is vastly harder than landing on solid ground. The ocean moves, the wind shifts, the target wobbles, but still, the rockets land with eerie grace on a floating platform the size of a basketball court, using only software and sensors. It's the aerospace equivalent of a gymnast leaping off a cliff and landing on a moving trampoline, flawlessly. This ability to land at sea expands SpaceX's mission range dramatically, and it means more boosters saved, more flights, more reuse, more progress. Landing is just step one. The true value of reusability lies in rapid turnaround. After a booster is recovered, SpaceX performs inspection, maintenance, and refurbishment. In the early days, this process took months. But with experience, they've cut it down to weeks, even days in some cases. They've now launched boosters that have flown 10, 15, even 20 times. These aren't experiments anymore. They're workhorses. And the data tells the story. A new Falcon 9 launch might cost $62 million. But with reused boosters, internal costs can drop below $30 million. That's nearly half the cost, and it keeps dropping as turnaround improves. In 2022 and 2023 alone, SpaceX performed over 60 to 80 launches annually, most of them with reused boosters. Reusability is no longer a goal. It is the norm. And this is how SpaceX has become the world's most prolific launch provider, outpacing all other countries and companies combined. Falcon 9 was the proof of concept. But SpaceX is already working on the next evolution, Starship. Starship is a fully reusable super heavy-lift launch vehicle, designed to carry not just satellites, but humans to the Moon, Mars, and beyond. Standing nearly 120 meters tall, it is the largest rocket ever built, more powerful than the Saturn V that took humans to the Moon. It's composed of 2 stages, the Super Heavy booster and the Starship upper stage. Both are designed to land and be reused, the entire system, not just the booster. And unlike Falcon 9, which uses carbon composites and aluminum, Starship is made of stainless steel, durable, heat-resistant, and surprisingly elegant. Its 33 Raptor engines on the booster and 6 on the ship itself run on methane and liquid oxygen, fuels that could potentially be synthesized on Mars. If successful, Starship could lower the cost of sending mass to orbit by a factor of 10 or more. Entire space stations, moon bases, interplanetary missions, reusable, scalable, audacious. Starship represents not just an upgrade, but a transformation in how humanity thinks about space travel. So why does this all matter? Because space is no longer the exclusive realm of billion-dollar missions and Cold War geopolitics. Thanks to reusability, we are entering an era of abundance. More satellites for weather, agriculture, and internet access. More missions for planetary science. More capacity for lunar exploration, asteroid mining, and eventually, Mars settlement. Costs go down. Access goes up. Entire industries, from manufacturing to tourism to deep space research, become viable. But more than that, reusability changes our mindset. It says, we can do better. We don't have to throw away the future. We can build systems that last, that evolve, that repeat.